Hello everyone. As OpenAI and ChatGPT are making inroads into various domains, today I would like to show how we can use it in digital ASIC design. In this demonstration today, I will take an example to use a spec written in plain English and convert it into RTL using ChatGPT with just one click. Here's the example problem statement that we will be using. It is a simple DC blocker. I will not go through what a DC blocker does. You can read about that online or even just ask ChatGPT about it. But this is the problem statement that we will be using for today's demonstration. I will change up the language used here several times later down the video just to show that we are in fact using an AI model and not relying on scripting to create what we are looking for. The process is demonstrated in this flow diagram here. We extract the parameters from this problem statement written in plain English, then obtain the coefficient required for the DC blocker, then convert it into a fixed point representation, which is what we will be using inside the RTL, and then we will generate the RTL. The generated RTL will be fully simulatable and synthesizable. I will be using Python to access OpenAI's API. If you want to learn about how to access OpenAI's API, there are a lot of videos out there on YouTube. You can check them out. Now, the text file here is what I have used to save the English language version of the specification. This is what I showed you on the Word document a while ago. We will be modifying this in many different ways just to demonstrate that it does not matter how we write the spec, the result will still be the same. Now, I will not go through the individual functions and prompts that I have used in this video. I will create a subsequent video to go through the right way of writing a prompt to obtain the desired results. That is what is called prompt engineering, and I will cover that in the next video. For this video, I will just demonstrate the potential that ChatGPT has for converting specification to RTL. With that, let's proceed. Now here you can see that I'm printing the problem statement as it is. This is what we saw on the Word document as well. You can now see that our DC blocker has been generated. I will open this file to show the contents. Here it is. You can see that all the code here is in the standard Verilog format. Now, if you work for any company, you can pretty much use a proprietary tool like NCSim or ModelSim to simulate this and make sure everything is fine. However, for the benefit of everyone, I will use an open source web application called EDA Playground. For that, I'm just gonna copy this code here. And paste it here. This is the web application whose link is edaplayground.com. Anybody can use this, you can check it out. We do have a free simulator here, and I just pasted our design here. This is going to be our design under test. For the sake of this video, I have already created a test bench here. You can see that I have the clock and reset signals along with an input, which is the DC blocker input. I have just set it to a constant of 1024. Now we will run this code and see how this constant decays at the output of our DC blocker here. I'll go ahead and run this code. Okay, now here we can see that the input is at 400. It says 400 because we have chosen hexadecimal format. Unfortunately, we don't have a decimal representation in this tool, but that's okay. Now, if you look at the output, you can see that it decays and goes down to 0 eventually. I will not go into the details of the settling time based on the coefficient here. You can read that online. As I mentioned, we will change the English language used in the specification. For this iteration of the change, I will still keep these 4 bullets, but in the next iteration, I will completely change the entire paragraph here. So I will now fast forward this change because I don't want to waste your time by showing the changes I'm making. Now the wording of the specification is completely different from the previous version, and you can see that I have also changed the data bit width and the coefficient bit width along with changing the cutoff frequency. This will be a bad DC blocker, but right now we are only caring about generating the desired RTL. So I will go ahead and run this code. The code has now successfully completed its execution. Now let's open the newly generated DC blocker file. You can see that the data width is 16 bits and the coefficient width is 12 bits. Now let's go ahead and copy this to run this in our EDA playground. I will now go ahead and paste our code here. You can see that the bit widths are different. We need to modify our test bench to accommodate those changes in the bus width. We can keep the same input as it is still within the range of our new data width, and I will now go ahead and run this code. As you can see here, our output starts at hex 400, which is 1024 in decimal, and slowly decays down to 0. Here we can see our bus widths are indeed different. Now they are 16 bits wide. The coefficient, which used to be 16 bits in the previous version, is now 12 bits wide. Now we will move on to our third example, where I will change the specifications completely to reword and reformat the language used and show you that the results generated will still be as good as the current one. For the third version of our specification, I have completely formatted the text that we use. I have described all the desired parameters in line 1 without any bullet points, just separated by commas, and I'm asking what to be designed only in the second line. This is completely different from what we saw in the previous 2 examples. Now I will go ahead and generate our RTL using this version and see what we end up with. We now have our finished code. Let's take a look. Okay, it looks fine. We can see that the data width is the new data width that we mentioned in our spec here, which is 32. Coefficient width we used was 20, and we have gotten that coefficient. And we also see that the coefficient that is being used is new. So let's copy this and run this in our EDA playground. I will go ahead and paste our latest code here. As you can see, we have a 32-bit data bus. So let's make the changes required in the test bench and then pretty much run. As you can see, our output goes from hex 400, which is decimal 1024, and decays down to 0 as how a DC blocker would do. This shows us that irrespective of how we write our specification in the English language, as long as we have the desired parameters well defined, we can generate the final RTL. With that, we have come to the end of this video. Please stay tuned for more videos and discussions on how to use ChatGPT and OpenAI's API for ASIC design. And until my next video, cheers and enjoy designing. Thank you.